Great. Good evening, everyone. My name is Ginger Sigmund, and I'm the Managing Director of ND Energy. Welcome to our seminar tonight. It is the kickoff event of a four-part series on advances in nuclear technology, where we will discuss the many ways nuclear is being used to generate power, preserve human health, and support universal discoveries. You can see the titles of our upcoming 3 talks and register for those events on our website at energy.nd.edu. And also on the website, you can find information on the Energy Studies minor and the other activities that we're doing at ND Energy. It is my pleasure to introduce our speaker tonight, Dr. Peter C. Burns. He is the Henry J. Massman Professor of Civil and Environmental Engineering and Earth Sciences and the Director of ND Energy. His talk tonight is going to look at fact, fiction, and the future of nuclear. So, Peter?
Well, thanks, Ginger, and thank you to everybody who has joined us tonight. I think I'm still having a problem with my projection. Sharing is paused. Okay. I'll get heavens. Don't worry, I have a backup plan. I just don't know what it is yet. Okay, this should work. Aha. Okay, very good. So thanks, Ginger, for the introduction, and thank you all for joining us tonight. I can see a nice turnout. A few of you I know are not anywhere near us in South Bend, so welcome from wherever you are. It's pretty cold up here in South Bend tonight, but we can all be thankful that we've got enough energy to stay warm, frankly. So the folks that organized this session asked me to speak specifically about advances in nuclear technology of today and the future, fact, fiction, and the future. So I decided to do exactly what they've asked, or try to at least. And my presentation will be split into 3 parts on fact, fiction, and the future. And my crystal ball is a little bit hazy relative to the future, but I'm pretty confident about some facts and fictions. And these won't be an all-inclusive list. But the first fact that's relevant to nuclear is Einstein's special theory of relativity, E equals mc squared. Second is that nuclear is clean, and I'm talking from an environmental perspective, and I'll back that up with specifics shortly. Another interesting and, well, important fact is that there have been major impactful nuclear accidents, and there's really been more than most people are aware, but the 3 that are certainly the most famous, 3 Mile Island, Chernobyl, and Fukushima. I'll talk a bit about what happened in those accidents to give you a sense of whether or not the following statement is fact or not, which is nuclear is a safe source of energy. And then some fiction. No level of radiation is safe for humans. Radiation causes birth defects in humans. There's no solution to nuclear waste, and there's not enough uranium to make it sustainable. I'm going to tackle each of those fictions head on and hopefully convince you that they're indeed just that, fiction. And then the future, advanced reactor designs and small modular reactors will receive some attention. So back to the beginning, E equals mc squared. Einstein's special theory of relativity, introduced in 1905, equates energy to the mass of material, of the mass of matter, to multiplied by the speed of light in a vacuum squared. And the speed of light in a vacuum is a really big number, and when you square it, it's even more. And so it's clear that if we knew how to convert mass to energy, we would have, well, effectively unlimited energy at our fingertips. Worldwide consumption of energy in barrels of oil equivalent as of a couple of years ago, and I don't think it's changed much, was 118,300,000,000 gallons of crude oil. So this is, we didn't consume that much oil, but we consumed energy equivalent to that much oil. Energy is stored in fossil fuels in chemical bonds, and we combust those chemicals in order to extract that energy. And of course, this also leads to emissions of CO2, amongst other things. If we could convert mass to energy by equals mc squared, we could obtain the same amount of energy from only 8,055 kilograms, which is 3.2 of the new Tesla Model X's per year. So if we could convert 3.2 Teslas to energy with 100% efficiency, that would meet the energy needs of the world per year, in principle. Of course, we have no technology to do so, but things started to change in 1938 when two scientists, Hahn and Strassman, found experimental evidence for the fissioning of uranium via neutron irradiation and proposed the possibility of a sustained chain reaction in a nuclear condition in a reactor. They weren't the first to come up with this idea. I think it had been around maybe about 6 years. Leo Szilard, I think, was the first to propose it, but they came up with some experimental evidence. In essence, what they found was if you had a fissile isotope of uranium, in this case it's uranium-235, and a neutron interacts with that nucleus, with the neutron traveling at the appropriate speed, you will convert the 235 nucleus to uranium-236, which is very unstable, and it basically explodes into two fission products, as well as additional neutrons. These additional neutrons, of course, can then cause the same reaction for another uranium-235. So it can be a self-sustaining chain reaction, and it can also be an out-of-control chain reaction if the conditions are right. And the applications, of course, are in commercial generation of energy with the controlled reaction and the uncontrolled reaction in nuclear weapons. Anyway, the point is that this nuclear reaction releases a tremendous amount of energy. And this is not like this primitive burning of fossil fuels where you release a little bit of energy that's been tied up in chemical bonds for millions of years, but rather it is conversion of mass to energy. If you add up what's on the left side, the neutron and the uranium-235 nucleus, and you add up what's on the right side, you'll notice they don't balance in terms of mass. This fission process has destroyed, well, 0.186 atomic mass units has ceased to exist. In fact, it's become energy, 173.3 mega electron volts. So there's an absolutely tremendous amount of energy available if we can split fissile isotopes in a safe and controlled fashion. One uranium fuel pellet for a typical reactor is about the size of the end part of your finger. A dime is given there for scale. If we reprocess and recycle spent nuclear fuel, and we use breeder reactor technologies, which I'm not going to talk much about, but I will mention again in a few minutes, but they allow us to convert the non-fissile isotopes of uranium, which are very far, in a way, they're most abundant in nature, to fissile plutonium and burn that. If we do both of those things, one fuel pellet will give us as much energy as burning 300 barrels of oil or 100 tons of coal, or 1.6 7 million cubic feet of natural gas. So the energy density, so to speak, of uranium is extraordinary. This is the nuclear fuel cycle. It's my own illustration of it because I never could find one I completely liked, but there are many different versions, but essentially the same thing. But we all know about nuclear reactors, of course. In fact, our electricity here tonight could very well be coming from the Cook power plant up at Lake Michigan. But we don't often think about the other parts of the fuel cycle. So what I have up here is what we call the front end of the fuel cycle, the parts of the cycle that occur before the reactor, and then the back end, which is essentially how you manage all the waste. So at the front end, first of all, you find uranium and mine it. It is possible also to run a thorium cycle, but in the US we currently don't. So you mine uranium, do whatever chemical processes you have to do to recover it and concentrate it. And then for an American style reactor, at least, we need to do enrichment of the 235 isotope. Out of the ground, uranium is 0.7% of the 235 isotope, and we enrich it in the 4 to 5 range for American reactor fuel. And that's done in centrifuges, normally using uranium hexafluoride. Then it's converted to an oxide, fabricated into a fuel, and it goes into the plant, the actual nuclear reactor. Fuel going into the reactor is essentially non-radioactive. It is mildly radioactive, but it's really there's really no safety issues. But during the reactor operation, where the fuel might reside for a year and a half to maybe 2.5 or more years, there's a tremendous change in its composition due to fissioning of uranium and also various other nuclear reactions that take place. And the fuel that comes out of the other side of the reactor is intensely radioactive, so much so that exposure to a fuel assembly would be lethal for a human in just a matter of seconds, really. So of course it has to be handled remotely and safely. And so on the back end of the fuel cycle, we put, first of all, the fuel into cooling ponds underwater. That provides the advantage of being able to transmit the heat away as well as provide shielding. So it's quite safe to walk up around above these assemblies under all this water. And then after around 10 years, these are retrieved from the cooling pools, dried, and put in above ground storage. Now in the United States right now, that's where we're at. All of our commercially generated fuel is in what we call interim storage or on-site storage at the reactors where it was produced. It's possible to close the fuel cycle, in which we chemically process the fuel, recover the valuable constituents, the fissile isotopes and uranium-238 that go back in the fuel cycle, as well as various lanthanides and various radionuclides that can be used in medicine and so on. And then we manufacture some sort of a waste form for ultimate disposal in a geologic repository. Although in the United States, currently, the policy is open cycle or direct disposal of commercial spent fuel without reprocessing. So that's the fuel cycle. And I want to come back just for a second to the reactor itself, which is, as I said, only a relatively small part of the cycle, but it's the one we know about because it's the one that produces the actual energy we use. And it's also where the most spectacular accidents have taken place. And the spent nuclear fuel in a reactor, first of all, it's really hot, thermally hot while the reactor is operating. And if you have to shut down the reactor for any reason, it's essential to continue to cool the fuel because there's enough radioactivity, very intense radioactivity in the fuel that it will heat the fuel. It will self-heat it to the point it will melt. So loss of coolant accidents are really the biggest risk in a nuclear reactor operation, loss of coolant, because the fuel can melt. The fuel melts, then the various radionuclides can be released. This shows one of two major designs that are in use in the United States today. The pressurized water reactor. The reactor vessel's over here, and it's got control rods and containment around it. And then there's another big containment structure. And there's one circuit of pressurized water that cools the core. And then there's a steam generator with a second cycle that drives a turbine. And then there's a third cycle that condenses that water to complete the cycle. So basically 3 closed loops of water. And this is a very safe design because the chances of water being released out here are very, very low. You'd have to have multiple failures. There's also the boiling water reactor. There's still a few of these left in the US. And it's a bit different because it only has 2 cycles, 2 circuits of water. You boil water in the reactor, creating steam that drives the turbine, and then that's condensed over here and sent back into the core. Okay, nuclear is clean. Well, it depends how you want to count clean, I suppose, but what we've all come to realize in recent decades, and especially in recent years, is that greenhouse gas emissions are a very major issue. And so certainly nuclear is extremely clean relative to the emission of greenhouse gases. And I give you here data from the literature. Basically, the amount of greenhouse gas emissions per gigawatt hour of annual electricity produced. And you might wonder why nuclear is not zero, because you're using a nuclear reactor. But of course, you have to also account for the construction of the plant, which used concrete, and you have to account for the mining of uranium and the enrichment and so on. So the life cycle, it's about 3 tons per gigawatt, whereas coal's 820. And wind and solar are very similar to nuclear, again, because they have to be constructed out of mined materials, transported, and so on. So coal and oil are the worst. Lignite is the worst of the worst, which is a subcategory of coal. Oh, natural gas is better, and it has less other harmful emissions, but it still releases plenty of CO2. Oh, and on the bottom right is a bunch of above ground storage casks. That's the other side of clean. Yes, of course, there's nuclear waste generated, and it's quite intensely radioactive for a long time. But I will argue tonight that that's not a barrier to expansion of nuclear, that we can, in fact, solve the waste problem. And thus far, all of the waste that's been stored at reactor sites across the country is still exactly where it was placed. You can compare that to the waste produced by the coal cycle, for example, which was pretty much all released to the environment, either as gas emissions to the out the smokestacks or coal ash. So the nuclear cycle has been vastly cleaner, and at least, amongst other things, keeping its waste exactly in containment. So a few words about some of the accidents that have happened, because that's always an area of debate and concern when thinking about nuclear energy. The famous 3 are 3 Mile Island, Chernobyl, and Fukushima. There's actually about another 18 or 20 pretty major nuclear accidents, but over the years, but some of them are not well understood and so on. They occurred in some cases on naval vessels in the former Soviet Union, for example. So we don't have a lot of details, but the big ones are here. And Fukushima was the most recent, 2011, Chernobyl, 1986, and 3 Mile Island, 1979. 3 Mile Island was the worst nuclear accident in the United States commercial generation history. One of the reactors there had a serious thermal excursion and was damaged and partially melted. And as I'll show you in a few moments on another slide, the use of water as a coolant in a reactor creates a certain vulnerability. And that is that if the temperature gets too high, the water can react, or the water vapor can react with the fuel cladding to produce hydrogen and oxygen. And then of course the hydrogen goes up into the top of the containment. And if there's a spark, you can have a massive explosion and lose containment. And so it's necessary, if you have this type of a partial meltdown, it's necessary that the containment actually be vented. And that was done at 3 Mile Island, and it was done properly as far as I know, but it did result in the release of radioactivity into the surrounding communities. And much emphasis was placed on that. Evacuation orders were put in place. Well, cost a lot to clean up the mess, but I don't believe there was a single death related to the radioactivity that was released during that accident. I knew one gentleman who led some of the technical response, and he told me that they actually couldn't detect the radioactivity downwind that came from the plant because the background was too high coming from the coal burning facilities, which also released radioactivity. Of course, they release the radioactivity during normal operations, a nuclear reactor only in very abnormal operations. Chernobyl was a different story, though. I said 3 Mile Island didn't result in any deaths. Chernobyl certainly did. Some of you maybe have watched the HBO miniseries in recent times. It's actually a pretty fascinating watch. And some of it is kind of accurate, and some of it isn't. Sorry, I don't know if you can hear it, but my computer dinging. Chernobyl. So Chernobyl was an RBMK 100 graphite moderated reactor run in the Soviet Union. It was in Ukraine, and it was an inherently dangerous design. In American reactors, some of which were maybe not that much better, because we did run, in the weapons program, we did run graphite moderated reactors, but in a typical water-cooled reactor, the water is a moderator and the coolant. So the water is moderating the neutron velocities in order to increase the reactivity while also providing coolant. And if you lose one, you lose the other. If your water all drains out, you don't have any more moderator. But the RBMK design has, it's graphite moderated. So you have solid graphite moderating the reaction and keeping it going, and water is a coolant. So if you lose your coolant, the reaction is still moderated, and that in itself is kind of inherently dangerous. But anyway, a series of unfortunate events led to a massive explosion that destroyed the core of the Chernobyl reactor and sent a huge amount of radioactive material into the atmosphere, dispersed several tons of highly radioactive core, and so on. Anyway, quite a bit of time has gone by, and various studies have been conducted, and the one I'm going to refer to now was done about a decade after Chernobyl, and it was done by the World Health Organization, and it was on the legacy of this accident. And what they found was that about 1,000 on-site reactor staff and emergency workers had received very high levels of exposure on day one, and that something fewer than 50, but close to 50 deaths were attributable to that radiation. Another 200,000 emergency workers received exposures over the next couple of years, cleaning up the site, building temporary sarcophagus. And it's estimated that about 2,200 radiation-induced deaths will occur in their lifetimes. And in 2005, there had been 4,000 cases of thyroid cancer in children, 99% survival rate, 9 known deaths. Otherwise, the World Health Organization team, and it was 150 doctors, found that they couldn't find any evidence for increases in the incidence of leukemia or cancer amongst the affected residents. And they found in the affected population no evidence or likelihood of decreased fertility and no evidence or increases of malformations due to the radiation. And instead, they found that the really big impact was from poverty-related diseases. We were at this point close to the collapse of the Soviet Union, mental health problems, relocation of 350,000 people, and terrible fears of radiation created, well, mental health problems that were far more severe than the radiation itself. Fukushima occurred, the Fukushima accident occurred in Japan in March 2011. There are 6 reactors at the Fukushima Daiichi plant site. This is reactor 1, 2, 3, and 4, and then 5 and 6 are over here. They're beside the ocean. On March 11th at 1446 local time, there was a magnitude 9 earthquake. The design basis of the reactors was magnitude 8. So they were designed to withstand anything up to an 8, but in fact, I'm talking Richter scale magnitudes here, and it's a logarithmic scale. So a 9 is 10 times more powerful than an 8. But nevertheless, the reactors performed quite well. They shut down automatically as designed, and everything seemed to be, under control until 1541, a tsunami triggered by the earthquake, which was underneath the ocean floor, struck the site, and its estimated height was 14 meters, whereas the design basis was 6.5. The tsunami completely inundated the site, flooded the basements, washed away fuel tanks, etc., and all on site, and power was lost. And you'll recall I mentioned earlier the need to cool a reactor core even after shutdown, and that's where the problem came out at Fukushima. Because of the loss of electricity and the inability to pump water as a coolant, the reactors were in danger of meltdowns, basically. And on the left shows a picture before, and on the right shows a picture taken after the tsunami, and you can see the containment on units 1 and 3 appears to be destroyed. And as I mentioned before, during the heat excursion, water interacted with fuel elements and the cladding, producing hydrogen gas that accumulated within the containment. And although I understand that some venting was done, it wasn't successful. And units 1, 3, and 4's containment were entirely destroyed by explosions. These were not nuclear explosions, they were hydrogen gas explosions, but they destroyed the containment, and now you've got exposed melting nuclear fuel basically open to the atmosphere. The exact details are basically similar. They didn't all explode at the same moment in time. They were able to cool some of them for a longer time than others, and it was a General Electric Mark I reactor design, and this is a schematic of what was there, and the secondary containment area up at the top was what was destroyed by these explosions, and the primary containment and the fuel core was impacted by the temperature excursion. The hydrogen gas was produced by the interaction of water with fuel. Fuel itself melts at about 26 to 2800 degrees C, which of course very, very hot. But you don't need to get that high to have the hydrogen problem. So there was a lot of misinformation, of course. There was a lot of panic. We were now pretty much into the internet age. Of course, people had information and so on. This is one of the things that was circulated on the internet within a couple of days of the the accident, and it's supposedly from the Australian Radiation Services, and it shows the magnitude of the plume that's going to settle upon America within 10 days. And it's interesting that, by the way, would be a lethal dose of radiation for pretty much everybody in the West Coast. And it obviously didn't happen. And I know folks that worked in Washington State, and they were able to detect fallout from this accident, but only with the most sensitive instrumentation and most careful measurements. I'm not arguing that fallout wasn't an issue, but this type of misinformation campaign can cause a lot of panic in the populations and can do a lot more harm than, well, it can do no good and it can do a lot of harm. So nuclear is safe. I've just told you about 3 major accidents. And so it might seem odd that I will now turn to the topic of safety, but there have been academic studies, not my own, of the safety of energy production. And so this is the number of deaths per terawatt hour of energy production. If you burn coal, you're looking at 24.6 deaths per terawatt hour. And if you're running nuclear, it's 0.07. This includes the whole life cycle. This includes in the case of nuclear, the accidents, the deaths at Chernobyl due to radiation. It also includes deaths in mining, transportation, and just planned operation that don't involve radioactivity. You get run over by a truck or whatever. So that's all in there. And coal, of course, it includes mining accidents and stuff too, but it's mostly respiratory illness that's caused by burning coal. And the quantity of that type of illness has declined in the United States, but you can be sure it's not the case in many parts of the world. Last time I was in China, there was only one day I could see the tops of the buildings in Beijing because of the tremendous smog, largely from coal consumption. So nuclear is very safe when you look at it overall relative to the amount of energy that can be produced and the corresponding number of deaths. An interesting study that came out several years ago now, 13, 14 years ago, for the average world consumption of 155,000 terawatt hours of energy per year, of electricity rather. If you generated that with coal, you could imagine attribute to it 3,797,000 deaths per year, and nuclear, it would be 8,200. So although nuclear is not without some risks, it is, I would argue, far safer than most sources of energy. Okay, no level of radiation is safe. Now we're moving on to fiction. I cannot say with 100% certainty that this is fiction, but neither can anybody say with 100% certainty it is fact, because there's no evidence, in fact, to really support either position. We don't have data on the health effects of low levels of radiation. We do know that for radiation exposures higher than about 100 millisieverts, it may be somewhere in the 100 to 200 range, health effects do start to appear, and they do get steadily worse with increasing dose. But when we go below that number, there's 4 possibilities shown here on this Canadian government diagram. One is hypersensitivity, where low levels of radiation, this is risk here, by the way, and dose here. So low levels of radiation are even more dangerous. Well, nobody believes that as far as I'm aware. This is the linear no threshold model, which just draws a straight line through the data and the origin. And then there's the more likely scenario here, where there is a threshold below which there's very little risk. And then there's even a fair number of scholars that argue that some radiation is helpful to your health, and that's the hormesis line down here. I don't know, like I said, I cannot definitively tell you which of these is correct, but I'm going to go with something down here. This is just, it's been adopted for regulatory purposes because it's simple. And it's simple to apply, and governments have used it all over the world. And it has led a lot of people to assume that no level of radiation is safe. But that is a myth. Humans have been living with radiation, of course, as long as they've been on the planet, long before there was any human-related activity that generated such radiation. Okay, this is the next slide is not very pleasant, but radiation causes birth defects in humans. When I Googled that on the weekend, just exactly there, human birth defects from radiation exposure, that is what my screen contained. Every one of these is a lie. You know, birth defects related to Chernobyl and so on, these are all lies, in fact, but that's what the internet gave me, such as it is. How do I know those are lies? Well, we already talked about the Chernobyl information from the World Health Organization, but more significantly than that even is what happened in Japan after the nuclear weapons attack. As you all know, the United States dropped 2 nuclear weapons on Japan near the end of the Second World War, on Hiroshima and Nagasaki. And very shortly after the war, the United States and Japan created a research foundation to study the radiation effects on the affected people. And not just them, but their several generations. This foundation continues to conduct research today, and you can go to their websites and see their most recent reports. So most people think that Hiroshima bombing killed everybody, but that's not the case. It killed about 100,000 people out of a population of about 250,000. What this created, not intentionally of course, but what this created was the biggest study of all time on the radiation effects on humans, because about 150,000 people survived, and this research foundation has been studying cohorts of those survivors and their descendants ever since. And they update their report every year or two. And what they found basically is radiation of 100 millisieverts at age 30 is increasing your chance by 50% of dying of cancer by 70. Association is in direct proportion for greater than 100 to 200 millisieverts. That's what we saw on the graph a moment ago from the Canadian website. For the higher doses, association remains unclear below about 100. So there's no data coming from this study that supports the linear no threshold model. And people with high doses, greater than 1,000 millisieverts, also have increased frequency of non-cancer diseases, cataracts, heart disease, and so on. But the question, or the myth I wanted to address really was radiation causes birth defects in humans, because that's the one we hear about so often as a negative side of nuclear energy. And I don't know if I can blame it on The Simpsons. I've heard of them. It's some cartoon, but I've not watched a single episode in my life, so I don't know if that's the cause. But according to this study of 150,000 or so survivors and their children, there are no inherited genetic effects from parent radiation exposure among the children of atomic bomb survivors. However, evidence at the University of Notre Dame clearly indicates that radiation causes birth defects in snowmen. And I give you here the evidence I also acquired from the World Wide Web on the weekend. I myself have gone to this location and thought about building a snowman. You all recognize this as the northeast corner of our radiation research laboratory. And almost every year undergraduates come up with this clever idea. No solution for nuclear waste management, for nuclear waste. That's another myth I will argue. First of all, we have solved it. These are pictures taken inside the waste isolation pilot plant in New Mexico, where nuclear waste is being safely disposed of about 2,300 feet below the surface in salt. This site has been operating since the 1980s. We don't hear much about it really, mostly because it's weapons related waste. It's not commercial waste, and as a result, what's the right word? The details are less public. But this site has been operating for a long time, and with the exception of one accident in which nobody was really hurt, in all those years, it's run rather well. The United States had a plan, and it was to dispose of our commercial nuclear fuel waste in Yucca Mountain, which is in Nevada. It's on the Nevada test site where nuclear weapons were tested. So obviously there's already a contamination issue there, because over 700 nuclear weapons were detonated on site. The first few above were atmospheric tests, and then they were underground. So it's already federal land, Federal Reserve, and so on. And I personally was involved in a lot of research to develop the scientific consensus that this site would be suitable. But politics got in the way. The Nuclear Waste Policy Act, passed by the US Congress in 1982, said, okay, we're going to go with disposal, geologic disposal of commercially generated waste. And that act was revised, amended in 1987 to lay out exactly how the process would unfold, specifically for the case of Yucca Mountain. So in 1987, the other sites that have been under consideration were taken out of the mix. And the process went along. A lot of scientists and engineers and other scholars too were involved, built a safety case. When George Bush was president, he approved the application to move forward from the Department of Energy to the Nuclear Regulatory Commission. Congress approved it, and that process was ongoing. The application had been submitted to the Nuclear Regulatory Commission, but President Obama came into office, and the man on the right, Harry Reid, turned out to be the second most powerful guy in Washington, now the leader of the Senate Majority Leader, and also from Nevada. And he had sworn, that if he ever got there would be no Yucca Mountain. And he had the power to make it happen. And so soon thereafter, Stephen Chu, Nobel laureate, third from the left, Secretary of Energy, announced that Yucca Mountain was no longer viable. And that was it. They dismantled it. And he didn't, of course, say it was no longer technically viable or environmentally viable. It was no longer politically viable. So, not enough uranium. This would be the argument that nuclear is not sustainable. It's certainly not renewable, because it is a finite resource, but is it sustainable? I suppose it depends on how you define it, but I will argue it is. So in our normal reactors in the United States, they're what we call thermal neutron reactors. We use moderators to slow the neutrons and decrease the probability of breeding in plutonium. We use moderators like graphite and heavy water and light water and so on. And it's mostly so we reduce the amount of plutonium that's being produced. And so in the US, all of our reactors are light water moderated. In Canada, the reactors are heavy water moderated. In both cases, the water is the coolant as well. However, it's also possible to run without a moderator or with different moderators and use fast neutrons to breed fuel. So uranium into the ground is 99.3% of the uranium-235 isotope, but that's a fertile isotope, which can be bred into plutonium-239, and that can then be burned in a reactor. So breeder reactors actually make their own fuel. And proponents will say, oh, they've never been proven and so on. Well, that's just ignorance. They have, in fact. Some of our first reactors operated in the US were breeders. The first reactor in the United States to generate electricity was a breeder. The picture showing there of the 4 bulbs that were lit, just as a demonstration. And there are breeders that have been running continuously in Russia, with new ones coming online actually within the last 4 or 5 years. So it's not such a mythical technology. So now we've got our current open fuel cycle where we run our uranium fuel through the cycle and call it waste to go to some unknown repository. That's not terribly sustainable, decades at most, certainly not into the hundreds of years. I think we have enough for a few decades. Closed uranium fuel cycle is when we recycle the fuel largely to remove the neutron poisons that grow in during reactor operation and allow us to use the fuel more, because the fuel's never actually really spent. It's just dirty and used. And then one can go to a closed uranium fuel cycle with breeders, and that takes you from hundreds of years of uranium supply to literally thousands. And then you also have the thorium fuel cycle, which I haven't talked about, but there's been a thorium demonstration reactor run in Oak Ridge in the 1960s in Tennessee. Thorium cycle has different challenges and different benefits, in fact, but there's even more thorium in the Earth's crust than uranium. So my conclusion is, if we take all of the energy that's used in the world and apply some kind of a reasonable growth curve to that, we can meet 5,000 years worth of energy needs of the world. I mean, all of the energy needs, all the electricity to run all processes, transportation, etc., if we took it to the extreme possible boundaries as we know them today. And I'll spend the last couple minutes talking about the future. As I mentioned earlier, I'm not as confident in my knowledge of the future as I am in some of the aspects of the past. But I do know a few things that I want to share with you. And the first is that nuclear power reactors have gotten steadily safer, more efficient, and the designs are significantly better, although we haven't brought a lot of those new designs to the market in the United States. Thinking of an analogy, it was possible to fly across the North Atlantic in the 1930s, I think, maybe commercially by the 1940s. And people did it, but we certainly wouldn't want to fly in one of those planes across the North Atlantic today. Instead, every cycle of airplane design and development made a safer and better airplane. And the same thing has been going on in nuclear since reactors were first built in the 1940s. But as I said, we haven't built the new fleet of ultra-safe reactors in the United States, but we do have the designs. And we've had scientists and engineers working on them continuously. And I might also note that the US Navy has been using smallish nuclear reactors since the 1950s on ships deployed all around the world, and has done so in a very safe and effective fashion. So we have a lot of technologies that could be brought to bear. And what we're working on now in the world really is what we call Generation 4 reactors. And you can see across the bottom the different countries that are kind of signatories in the research agreements, moving some different areas forward. Sustainability is a major emphasis, and that means using your fuel wisely. That means reprocessing. It means breeder reactors. It means, basically taking the uranium we've already mined and reusing it over and over and over again, and at the same time greatly minimizing the waste and the long-term burden associated there with that waste. I think it's pretty much a given. We've got to move away from water as a coolant. That's a major risk of nuclear accidents because of the adverse chemical reactions that produce hydrogen gas. And there are a lot of studies underway that are demonstrating really good ways around those problems. And that includes gas-cooled reactors, lid-cooled reactors, molten salt reactors, sodium-cooled fast reactors, and so on. I don't think there's any real need to go into all these details, but rather I'd like to spend a moment kind of painting a maybe a broader picture of what I think is possible in the not too distant future. And that will be the introduction of small modular reactors. These will be Gen 4 reactors that have inherent safety. They will not require active cooling. They'll be passively cooled. They won't require electricity and pumps and so on in order to keep them from melting. They will be small enough to be transported on a truck, although in the illustration it's not a small truck. But the idea is, don't go to a bunch of different locations and build reactors. Build the reactors at centralized facilities, factories, where you concentrate the expertise and you build them and you transport them to the sites where they will be assembled into larger reactor parks. And one of the ideas that makes, well, one of the aspects that makes this idea especially appealing is it streamlines the process of regulatory compliance. You will no longer have a lot of different reactors under construction. Well, it hasn't happened in some time in the United States. It is happening elsewhere in the world now, but you'll no longer have a bunch of different reactor designs, all of which have to be licensed separately. But instead, you'll have a small number of companies producing these under single licenses. And then they can be combined into a scalable source. So this is like an artist's rendition of what a plant might look like, where you can have several different small modular reactors in working together, or you could just have one, or you could have even more as the need might exist. And I don't think these are that far off. There are companies in the testing stage now. I think we could dream kind of big and say we might be able to have a nuclear powered University of Notre Dame in 20 years and achieve zero emissions, zero CO2 emissions. I don't think that that's an impossible scenario. I guess I better stop, so there'll be a little time for any questions or complaints or observations, or anything's welcome.
Thank you, Dr. Burns, for a very informative talk. I'd like to open the floor for questions. If you'd use the raised hand function that's found on the participants tab at the bottom of your screen, I'll call on you to unmute and ask your question. Okay, Isabel?
Hi, Dr. Burns. Thank you for the presentation. I think for me it was very informative. So if the Yucca Mountain project is not available anymore, where are the waste, all the waste is going right now? Where is it going?
Okay,
and only to New Mexico?
well, there's two. Isabel's in New Mexico. I know I'm on her PhD committee at the University of New Mexico. The current situation is that all of the commercially generated used nuclear fuel remains at the reactor sites where it was produced in interim storage. And then there's another couple of major categories of waste. One of them is the so-called tank waste, which is high-level radioactive waste caused or generated through the recovery of plutonium for nuclear weapons during the Cold War. And that material was stored in storage tanks, below-ground storage tanks at different sites in the US, the most significant being Hanford in Washington State. And it is a federal government's policy that that waste will all be removed from the tanks and turned into a borosilicate waste glass. And that will go also to the national repository that doesn't yet exist. So that glass is being manufactured at Savannah River in South Carolina, and it's all being placed in interim storage, awaiting a final repository. The waste isolation pilot plant in New Mexico is specifically for transuranium, or basically plutonium waste, from the weapons program, but not that really high, nasty radioactive stuff from the tanks. but rather stuff produced by refining of plutonium and contaminated instruments and gloves and so on. And so, but there's this, the regulations have changed, but over the years, but the waste isolation pilot plant in New Mexico will take a lot of plutonium related waste before it's finally closed. There have been discussions about expanding that facility to include commercial nuclear fuel. I don't know if those discussions are progressing, but I've heard the subject brought up at different levels. One of the issues is buoyancy because the disposal is in salt, and salt is kind of plasticky under pressure, and that can be a plus and a minus. It can be a plus in that it will flow in and encapsulate any waste after repository is closed, but it could also maybe be a minus, especially if the waste is thermally hot. You can imagine it might move out of the desired locations and so on. And so I think it's a little bit complicated. Yucca Mountain, of course, is still there. And it's still actually the law, right? It turned out that the Secretary of Energy canceled the project, but the court said, well, you can't do that because Congress passed a law that has a process that doesn't include the Secretary of Energy canceling it. So the current or future administration could choose to refund and move forward with that program. Of course, the downside is that there were literally hundreds of highly skilled women and men working on the project that all went and got other jobs elsewhere and stuff when it closed. So to rebuild the expertise to move it forward would not be a trivial task.
Thank
Right.
you.
The next question is asking about the types of nuclear plants that are being built in China. So can you comment on if you know if they're the modular reactors or what type of reactors they're building?
Well, I've never visited one or seen any of the designs, in fact, but my understanding is that they're larger scale plants, more similar to what we've built in the past than they are modular, but I really don't know the details. I've never seen one.
Okay, Ani?
Yeah, thank you, Peter. I'm very excited about the small modular reactors, particularly when you said that maybe Notre Dame will have one soon. The US just approved one of the first designs a couple of months ago. Do you have any idea of what the prices are?
I do not, Ani. I could give you a kind of, what's the right word? I mean, I could say we can't afford not to do it,
Oh, yeah.
but I'm not sure everybody would agree. I've looked at all the numbers, and in northern Indiana, how do we power our economy and a university based solely on renewables? I actually don't think it's possible to do that unless we dramatically curtailed our activities in some ways. So if we want to cover transportation and heating of our buildings and keeping our instruments running, et cetera, and we want to get to carbon neutrality, I think that nuclear has got to play a big part in that. Maybe not forever, but for the next few decades anyway.
No, I'm in full agreement about that. And I was very happy that we're finally moving in that direction in the US. As you know, Europe has been very actively pursuing the modular reactor concept a lot longer than we have. And I really think it's a fantastic idea to have a centralized building and centralized delivery than decentralized use.
I think they could even be delivered fueled and ready to go. And depending on the details of the design, they might run for 20 years and then be taken back to the factory for defueling, refabrication, and redeployment. And so there's no need to fuel on site or anything.
I mean, that's the attraction, because then it's all completely clean. Deliver, use, take away, with no local waste issue. So I'm really excited about them. Thank you.
All right, and we'll throw our last question out to Hachitar.
Thank you very much, Peter. It was really interesting, entertaining, and informative talk. So I learned a lot, and I have one question regarding this metal-cooled reactors. So this becomes interesting, like sodium and lead. So why, like, different countries are concentrating on different types of the coolants? Is there a basis, or is there a reason why they're doing this? Like Americans, they want the lead related stuff. I think Russians do sodium, right? Is there a reason why this is the disagreement?
Well, that's a good question. There's, well, I can say a little bit about background things. The EBR1 and EBR2, which were experimental breeder reactors 1 and 2 in Idaho, were sodium cooled. There was a molten salt. It was a fluoride molten salt reactor run in test mode in Tennessee. So there have been different plants explored in the United States. I know that the Soviets developed lid-cooled reactors relatively early on, and it strikes me as kind of interesting. They used lid-cooled reactors on nuclear submarines. I generally wouldn't have thought of putting a lid on a submarine, but apparently you don't need that much of it. So, you know, I'm not a nuclear engineer, so I don't know the fine points of the designs and the pros and cons. But of course, when you're thinking of a small reactor that's going to run maybe for 20 years with minimal intervention, no refueling and so on, there are so many issues, that technological issues that have to be mastered pertaining to the behavior of materials and the effects of radiation on the materials, and the corrosion at the interfaces between the coolant and the materials and stuff. So I know that each of the different coolants present a different set of complications that I really don't know why some countries have gone one way or another. It may be more chance than anything else. You get a very vocal engineer or scientist leading the project, and he says, "This is what we have to do," and then that's what you do, and you don't know why after a few years.
Thank you.
I know the fast reactors in Russia are sodium cooled, in fact. Yeah.
All right. Well, thank you all very much for joining us tonight. I hope you can join us next week for our second part, which is looking at a moral imperative of using nuclear power. So if the undergrads would like to stay on a few minutes and talk with Dr. Burns, I'm sure he can stay with us just a few more minutes. If not, I'd like to say have a good evening.